Okay, so now we will begin the semantics of logical operator. So semantic means the study of meaning. So each atomic formula has a truth or false value in the real world. Okay, so not every sentence is true in a world. Okay, so therefore each well-formed formula has a truth or false value in a real world, or so maybe in some imaginary world A. Okay? So it does depend on the world. Okay, so the the truth value of the well-formed formula depends on the truth value of the atomic formulas. Okay, so this is where the truth table comes in. So truth table generators, you can see these kind of things. So there are even ones which are programmed here, and there are actually many choices here, and so one has to learn some notation. Sometimes 0 or 1 is used instead of false and truth. Okay, so let's try to go to this Wikipedia article here. Okay, so logical identity is just P has the same value. Negation means that if it's true, then negation has a false value, and the truth value. If you have a false value, then it will be true here. So on. So it is, of course, they include lots of more things, but we are just interested in logical conjunctions like this. So both are true, then it is true. If any one of them is false, then and P and Q is false here. And disjunction is or here you have at least one of them is true, then it is true here. And logical implication is that the P implies Q is that if you have a truth for Q, then it is true, and if both are false, it is also considered true. Okay, so if Q is false, and if you have the false assumption, then this is true. Okay, so that's a kind of a convention. So that's a kind of a decision made by Russell and the Western philosophers. Okay. So we also have things called exclusive disjunction and then also these kind of things. These are all built from these logical connectives imply or and, so we will not be concerned with these. Okay, and you can build a truth table from the elementary ones. So the elementary ones are this imply or and and maybe these and then the negation. These four are the elementary ones, and so the way to build it, for example, is here. So maybe you can see. Suppose you want to understand the value of this sentence. What you do is you have to first write PQ and write down what not P and not Q. So true, false, false, true, false, true, false, and not P has this value, not Q has this value. So then you can write or not P or not Q case using this. So these two are false, so it's false. One of them is true, so true, true. So you can build value for this, and maybe you can even build many things in this way. Okay, so here there are some other examples. Here. So you can actually compute any value of the well-formed formula using these kind of methods. So let me show you these examples. Okay. So elementary ones are negation and, or, and imply. Okay, so every other logical operators can be built from these. So left right arrow implication or if operator is actually built from is equivalent to this, so it is not the elementary one. So you only consider these four to be the elementary ones. Every waveform formula can be evaluated from this if you know the truth table of these four ones. So sometimes in computer science you use SOR or NAND, but we will not be using this. So to construct the truth table for a complex WFF, we find the truth table for its smallest sub WFF, and then you use a truth table for the logical operators to get the value for larger sub WFF and so on. So you keep building it. So so let's try to build some here. So we have if you go to this site, then so there are many other sites, but let me try first with this. So A, B, okay, so A and B and A is depend on B, so it is if both are true, then it's true, and both are false, it is true. But if any one of them is true and false, then these are not true. Okay. And so let's try A, B, and B, A. Okay, so let's try that. So here it is written more divided way. So if A imply B, you will get this here. B imply A, you will get this. So and then there's AND operator, so you will get final result is 1 1 is 1, 0 1 is 0, 1 0 1 is 0, and of course 1 1 is 1. So this will be the value that we computed for A even on B also. So let's try this one here. So not G by not M imply M imply Z. Okay, so let's execute that. So ZM has these values: true, true, false, false, true, false, true, false, and so this one, not G, has this value, not M has this value, and this imply has 1 1 0 1, and M imply Z here. So this is the value here. So we compare this column with this column. So we get 1 1 is 1, 1 1 is 1, 1 1 0 0 is 1, and 1 1 is 1. So it is always true. Okay, so this sentence is always true. Okay, so maybe let's go compare with these two. Okay, so let's say P imply Q. Okay, P imply Q. Okay, so that's an elementary one. Okay, so we compare that to not P and Q and Q. Okay, so you get not P is this, and you compare it with the Q here. So 0 0 0 0 0 1 1 is 1 1 0 is 0. Okay. But now let's replace this with OR. Okay, so let's say function. Okay, so then you get this here, so 1011. So it is the same as P imply Q. So one true is true, this is false, this is true, and 00 is also true. Okay, so actually, so you can show that this sentence is true. Okay, so this one you can check. So this is equivalent to this part is equivalent to this part. That's what we are trying to show. So let's say P implies Q, not P or Q. Okay, so let's execute. So as you can see, it is always true. So you get the same value of the logic here, so you get the same copy here. So therefore, it has to be the same. Okay. Okay. So you can do many of these kind of logical table games here, and so you can also do XOR or these kind of things. So tautology and contradiction. So given some formula, any assignment of true or false gives true in the truth table. So such a formula is said to be the tautology. So for example, this one, and when you have a formula, any assignment gives you false, then this is called a contradiction or truth functionally inconsistent. So something like this. Okay, so let's go and try this. Okay, so P and not P. Okay. So the result is always false. Okay, so this is so you cannot have this kind of situation. Something is and then something is not. Okay, something is and something is not. So that's always true. Okay, so you can see that P or not P, so that's always true. Okay, so that's always true. So let's go to the next slide. So formula which is not one of the above is said to be true functionally contingent. So it means contingent means it depends. Okay, so it depends on the true or false value of the situation, whether something is true or false. Okay, so this is something which happens many times. Okay? So for example, you look at this sentence. That one was always true, so this was what you call the tautology, and that one's always tautology. And let's look at this one. So for example, let's try that. Okay, so we will check on this statements and see what this is. So I write down the Q imply R, imply P imply R. Okay. So let's execute. Okay, so in fact this is not always true, but this case where P is true but QR is false, then this one doesn't hold. Okay, so that's because this is true, but there is a case where this is true but this is false. Okay, so what that happens is when R is false and so on. Okay, so next I will do the next sentence. So truth table for argument forms. So suppose we have some number of premise and you want to get the conclusion Q. So we just need to check the validity of this kind of sentence. So say PIs are complex. So what we need to check is if every PI is true, then we just have to check that Q is true. Or you can form this sentence to check the validity of this thing. So if you want to deduce some things, okay. So let's say P imply Q and P imply not Q, then it is not P. Okay, and so to deduce the validity of this argument, you have to check this. Okay, so P imply Q and P imply not Q imply not P. Okay. Okay, so let's try that one. Okay, so so this is always true. So for this connective, you see that this is always true. So it is a theorem. So okay, so let's look at the last one. R imply P if and only if P or P and Q. Okay, so so let's go here. So we have already written this down here, and so let's execute. So you can see that this is always true, and so the reason it is true is because this side is actually always a tautology. Okay, so it's always true. So if you have anything and then anything which is tautology, this will be always true. So anything will in fact imply the tautology here. Okay, so this is true because this is a tautology. So thanks for listening to my third lecture, and we will continue.